We'll start with a graphic that we've had before. Population described by population parameters, and those parameters are constant but frequently unknown. And we have a sample described by sample statistics, which vary from sample to sample. That just means that one time you take a sample of a particular size, you might get a mean of 7. Another time you might get a mean of 7.4, 6.3, and so on. At any rate, it varies from sample to sample, and the statistic you get is a function of the particular sample that you happen to draw. We will, though, use those statistics based on a single sample to estimate and test hypotheses about those population parameters. This chapter and the central limit theorem are about making that connection between statistics and parameters. Well, one of the things we're going to talk about is sampling distributions, which are just a distribution of sample statistics. And those are bell curves if we just take a sample size that's large enough. We'll talk a lot more about this as we go through this presentation, but there's the basic idea. We're going to have bell curves if the sample size is large enough, even when the population is not normal. So now think about that. We're going to have a sampling distribution that's a bell curve. We're going to be able to use z-values even when the population is not a normal distribution. The central limit theorem is the foundation for statistical procedures like hypothesis testing and confidence interval estimation. And it's important because we don't have to have a bell curve for the population, because the distribution of sample means will be a bell curve if we just take a large enough sample. So let's start with a numerical example so we can get a better idea of the concepts involved in the central limit theorem and some definitions as well. Well, we're going to start with a population that consists of 4 values, 3, 4, 6, and 7. We're going to compute the mean of that population. Just add up the x's and divide by the size of the population. So 20 divided by 4 is 5. And naturally, along with the mean, we're going to calculate the population standard deviation. We're going to get the deviations. Each value of x, subtract the mean, then square those deviations. Then take the square root of those squared deviations divided by n. That's the population, so we're not subtracting 1 from n. This is the size of the population. And so we end up with a population standard deviation of 1.581. So now we're going to take every possible sample at size n that can be taken from the population. The example we're going to use here, we're going to take every possible sample of size 2 from that population. For example, we could draw 3, put the 3 back in, get another 3, or we could have drawn a 3 followed by a 4, or 4 followed by a 6, and so on. So here we have a list of all the possible samples, all the way from a 3 and a 3 down to a 7 and 7. You can see there's 16 of those samples. Again, this is just a list of all the possible samples of size 2 that can be drawn from our population. Right, note that the size of each sample is n equal 2, and the number of samples is m, and that's 16. So now we're going to compute the mean for each sample. So in the first sample we had a 3 and then a 3. The average of those is of course 3. In the next sample we had observations of 3 and 4, and the average of 3 and 4 is 3.5. The next sample we had a 3 and a 6, and the average of 3 and 6 is 4.5. Just add them up. 3 plus 6, divide by the number of them, that's 2. And you got 4.5. Now we're going to compute the mean of the sample means. An important thing has happened here. The sample mean now has become a random variable itself. And now we're going to compute the mean of those sample means. So we're going to add up the 3, the 3.5, the 4.5, and so on. And of course we're going to divide that by the number of them. So you add those up, you get 80. There's 16 of them. 8 divided by 16 is 5. So we get the mean of the sample means, mu of the x bars, that's the mean of the sample means. And we have the sum of all the sample means from all possible sample size 2. The number of samples is m equals 16. Well, so here's rule number 1. The mean of the sample means equals the mean of the population. And we had a population mean of 5. Now we have a mean of the sampling distributions that's also equal to 5. Now I'll go ahead and note here that we won't always know the mean of the population. When we do, we can say the mean of the sampling distribution is the same thing. But even when we don't know the mean of the population, we might hypothesize a value for the mean of the population. That's how we're going to get into the hypothesis testing procedure. Populations and for specific samples, we compute the standard deviation. For sampling distributions, in part just to mark out the difference between population samples and sampling distributions, we're going to call for sampling distribution, we're going to call the standard deviation the standard error for the sampling distribution. And that's going to tell us how spread out the sampling distribution is. Again, the sampling distribution is the distribution of the statistic, in this case x bar. We had those 16 x bars, we got the center of them, and now we're going to talk about how spread out they are. Okay, the symbol is sigma x bar, the standard deviation or standard error of the sample means. Later we'll have other statistics there, so we'll have the sigma, we'll have a subscript of, for example, p hat. So we'll have sigma p hat, which will be the standard error for the sample proportion. And here's our formula. Looks a lot like our formula for standard deviation. We take each x bar, subtract the mean of the x bars, square the deviations, divide by m, and then take the square root. So now let's compute that standard error. We're going to compute the deviations, subtract the overall mean, 5, from each of the sample means. So we've got 3 minus 5 is minus 2. 3.5 minus 5 is minus 1.5, and so on down the list. Then we're going to square each of those deviations. Minus 2 squared is 4, minus 1.5 squared is 2.5, and so on. We're going to sum the squared deviations. Just add all those up, we get 20. Then we're going to divide the sum of squared deviations by m, the number of sample means. Then we're going to take the square root. And we end up with a standard error of 1.118. Now let's look at standard deviation for a population and the standard error for the related or associated sampling distribution. Unlike means, the standard deviation and standard error are not equal. In this case, we had a population standard deviation of 1.581 and a standard error of 1.118. However, there is a mathematical relationship between the two, with the standard error being equal to the population standard deviation divided by the square root of sample size. Okay, so rule number 2, just to repeat, the standard error of a sampling distribution is equal to the population standard deviation divided by the square root of sample size. Now, sample size, the size of each sample, in this case that was 2. It's not the number of samples. In fact, you'll hear me repeat it again, and maybe again, that we're looking at the size of the individual sample n. And that's what's going to affect things, as you'll see later on, not the number of samples. Let's draw a graph of the population. Remember, our population consisted of 4 values, 3, 4, 6, and 7. So here's just a graph of that. Each value occurs once and only once. So we just have a uniform, just a flat distribution with values at 3, 4, 6, and 7. Now let's graph the sampling distribution. First, I'm just going to turn our sampling distribution into a frequency distribution. I'm just counting the number of sample means that are 3. There was one of them. There were 2 3.5s, 3 4.5s, 4 5s, and so on. So that's going to be our sampling distribution. Now here's a graph of that. This is no longer a flat distribution. In fact, sort of has the makings of a bell curve. And that really is the heart of the matter. So let's look at those two graphs just together. Population, a flat distribution. It's the distribution of X. The sampling distribution is a distribution of sample means. Remember, we took the sample mean of 16 samples, which were all the possible samples of size 2 that we could take from that population. Then we made a distribution of those sample means. It's starting to look like a bell curve. So, sampling distributions tend to be bell curves. The key is going to be to take a sample size that's large enough, because if it's large enough, the shape of the sampling distribution for many statistics will be bell curves. Specifically, for the sample mean, if we have a large enough sample size, the shape of the sampling distribution will be a bell curve, and it will have a mean of the sample means equal to the mean of the populations, and a standard error, the sigma x bar, equal to the population standard deviation divided by the square root of n. Taken together, this is the central limit theorem. The idea. The sample size is large enough, the shape of the sampling distribution for many statistics are bell curves. And that's important because it connects statistics from a single sample to related population parameters. Specifically, it's going to allow us to use z values from a normal curve even when the population itself is not a bell curve, because the sampling distribution will be a bell curve. Now we'll come back to our usual graphic here. We've got the population described by population parameters, which are constant but usually unknown. We have a sample described by sample statistics, which we can compute from a sample and which vary from sample to sample. Typically, we're going to take one sample, compute the statistic from that sample, use it to estimate the population parameter. That connection is going to be via the central limit theorem, which helps us understand that statistics vary from sample to sample in a systematic way. Specifically, the sampling distribution is a bell curve. Okay, let's just get to a first application here. We're going to use the normal table to compute probabilities for sampling distribution. The average American watches television for 10.8 hours a week. The population standard deviation is at least close to 4 hours. We don't know the shape of the population. And that really doesn't make any difference because the sampling distribution will still be a bell curve. So let's say we take a random sample of 100 Americans. We will know how likely it is that the average number of hours an American watches television in a week is less than 10.4 hours. So we started with a population mean of 10.8, and now we want to know in this sample, what's the likelihood that the average is going to be less than 10.4. The sampling distribution is going to be a bell curve. And with n equal 100, the sample size is definitely large enough, even if they're extreme values. Here's our bell curve. We have a mean of 10.8. You can see I've already shaded in the area that's less than 10.4. Notice that the label on my axis is now x bar. This is sampling distribution, the distribution of a sample statistic. Now our standard error, our measure of variability in this sampling distribution, is sigma divided by the square root of n, in this case 0.4. It's not the 4 from the population standard deviation. You got to divide by the square root of n. Then we compute our z-value in at least a similar fashion as we had before. We take x bar, which is now our random variable, minus the mean of the distribution, the mean of the sample means, and divide by the standard error. That all comes out to be 1, and we know by now that that means the area is 0.3413, the area from 10.4 to the mean, which is 10.8. But we're looking at the area below that, so we're going to subtract that from 0.5. So we're still with that average or population mean of 10.8 and a population standard deviation of 4 and an unknown population shape. Take another random sample of 100. We know how likely it is that the average in the sample is over 12. So we've got our sampling distribution, and I don't know if you can quite see it. I can. Starting at 12, I have a little blue shading there. That's the area we're after. Well, our z, x bar minus the mu x bar divided by the standard error, is 3. That's associated with an area of 0.4987, and that leaves out in the tail an area of about 0.0013, or you can think of that as close to 0. There's almost no chance we would get a value of 12 or more if the population mean is 10.8. Again, there's almost no chance we will get a sample mean that's over 12. That's really going to take us into the idea of hypothesis testing. We're going to start off, we don't know the population mean is 10.8, but we want to test the plausibility of a hypothesis that the population mean is 10.8. Again, we have the population standard deviation of 4. Then we collect data. And let's suppose that we collect 100 observations and get a sample mean of 10.8. As we've calculated just a minute ago, the probability that we obtain a sample mean this low or lower is almost 16%. Remember 0.1587, or 1 standard error below the mean. So if the real population mean is 10.8, we'd get this result 16% of the time. That's fairly often, so we're going to say that that hypothesized mean of 10.8 is plausible. Now with our second example, again we got a sample of 100, we got a sample mean of 12. And the probability of getting a sample mean that high or higher when the population mean is 10.8, it's almost 0. Remember we had 0.0013 So if we had a real population mean of 10.8, we'd almost never get this result. So now we've called into question that hypothesized mean of 10.8. In fact, we're probably going to conclude that the population mean is greater than 10.8. We got so far away. But there are two possible explanations for getting a sample mean of 12. First, this could be one of those rare times, about 1 in 1,000, 0.0013, could be one of these rare times that we really do get a sample mean of 12 when the population mean really is 10.8. It's possible. Alternatively, the population mean is not 10.8. Instead, might be some value greater than 10.8. Can't be certain, but we can be confident. We'd bet on it. Well, that's the logic of what we're going to do for the rest of the semester, or part of the logic for what we'll be doing the rest of the semester. Moreover, okay, now let's take a look at confidence intervals. When we develop interval estimates, we don't start with a specific hypothesis about the population parameter. Instead, we just start with data, then we calculate statistics from that data and use those to estimate the population parameter, or the corresponding population parameter to be more exact. For now, let's not think too much about the data or computations. We'll get to those. But let's think about the idea. We've all seen these political polls where you might say that 52% of those polled favor a particular candidate. What we want to know is that enough to conclude that that candidate is ahead and that we can be confident of that? Well, maybe. Again, remember that statistics vary from sample to sample, and this is only one of the possible samples. Other samples might lead or support other conclusions. We might get 53%, we might get 48%, or so on. Notice that 48% would lead to a different conclusion, but still could be one of the samples that we might draw from this population. So what we're going to do is we're going to use the fact that the sample that we drew, or the statistic we computed, comes from a bell-shaped sampling distribution. Using that idea, we can compute a margin of error. Again, we'll get to the computations later, but we're going to end up with something like this. We'll have an estimate of the population parameter, and it's going to be the statistic plus or minus the margin of error. In other words, in this 52%, we might have 52% plus or minus 3%, or plus or minus 4%. You can see 50%'s in there, and so the candidate might or might not be ahead.
Coefficient, which is going to be a z-value,
and we're going to get that, just to give you an idea, by multiplying standard error by a confidence coefficient, which is a z-value, which we can use because the sampling distribution is a bell curve. Well, for the rest of the course, fill in a few